Welcome to this comprehensive guide on Unity networking, where we'll explore the fundamentals of creating engaging multiplayer games. We'll delve into the essential components that make real time interaction possible, laying a strong foundation for your game development journey. We'll define core concepts like RPCs, sync vars, and network variables, which are absolutely crucial for synchronizing game states and actions across different players in a networked environment. Understanding these will be key to building dynamic and interactive multiplayer experiences. Understanding these elements is vital for developing robust multiplayer experiences in Unity, ensuring smooth and responsive gameplay that keeps players immersed. Without a solid grasp of these concepts, your multiplayer game could suffer from desynchronization and a poor user experience. We'll specifically focus on Unity's netcode for game objects, a free and straightforward solution for building your multiplayer projects. This powerful framework simplifies many of the complexities of network programming, making it accessible even for beginners. At the heart of Unity networking lies the client-server model, a foundational architecture for managing game interactions. This model dictates how different players' machines communicate and share information to create a unified game world. The server is responsible for maintaining the authoritative game state, acting as the single source of truth, while clients connect to it to participate and receive updates. This ensures fairness and prevents cheating by centralizing critical game logic. A host acts as both a server and a client simultaneously, a common setup for smaller multiplayer games or local testing. This hybrid role allows a single machine to manage the game logic and also participate as a player, simplifying deployment for certain scenarios. Briefly, network topologies influence how your game communicates, impacting performance and scalability. Different arrangements of nodes and connections can significantly affect latency and the overall responsiveness of your multiplayer game. Remote procedure calls, or RPCs, are functions that can be executed on a remote machine, enabling client-server communication. They are a fundamental mechanism for triggering actions or events across the network, such as a player shooting or interacting with an object. There are two main types: server RPC, called by clients to run on the server, and client RPC, called by the server to run on clients. This distinction is crucial for directing the flow of information and actions within your network game. To create a server RPC, you'll define a method in your network behavior script and mark it with this server RPC attribute. This tells Unity's netcode that this method should be executed on the server, regardless of which client initiated the call. This allows clients to request actions from the server, such as moving a character or firing a weapon. The server then processes these requests, validates them, and updates the game state accordingly, ensuring all players experience the same outcome. Conversely, client RPC methods, marked with client RPC, are used by the server to send updates or commands to specific clients or all clients. This is how the server propagates changes and events back to the players, keeping their game instances synchronized. For instance, the server might use a client RPC to inform all players about a game event, a score change, or to trigger a visual effect on their screens. This ensures that all participants are aware of critical game state changes in real time. All RPC implementations require your script to inherit from network behavior, providing the necessary networking functionalities. This base class is essential for any script that needs to interact with Unity's netcode system for multiplayer operations. While powerful, RPCs have limitations and security considerations. Always validate client data on the server to prevent exploits. Trusting client input blindly can lead to cheating and an unfair game environment, so server-side validation is paramount. RPCs are ideal for executing events that need to happen on all clients or between specific parties, like a chat message or a spell effect. They are best suited for discrete, instantaneous actions rather than continuous state synchronization. Sync vars are variables automatically synchronized from the server to all connected clients, ensuring consistent game state. When a sync var's value changes on the server, that change is automatically propagated to all clients, keeping everyone on the same page. You declare a sync var using the sync var attribute, making it a network-aware variable. This simple attribute transforms a regular variable into one that Unity's netcode will manage for synchronization across the network. This automatically synchronizes the variable's value from the server to all clients whenever it changes. This passive synchronization is highly efficient for maintaining consistent data across all game instances without explicit RPC calls for every update. Syncvars can hold basic types like integers, floats, unity types such as vector3, or even user-defined structs. This versatility allows you to synchronize a wide range of data, from player health to object positions, with relative ease. You can also use hook functions specified with syncvar to execute code when a syncvar's value is updated. These hooks provide a way to react to synchronized changes on the client side, such as updating a UI element. These hook functions are called on clients when the syncvar receives a new value from the server. This allows for dynamic visual or gameplay updates in response to server-driven state changes, enhancing the player experience. However, syncvars have limitations, such as monolithic updates for structs and a maximum of 32 syncvars per script. Understanding these constraints is important for efficient network design and avoiding unexpected behavior in your multiplayer game. Syncvar hooks are crucial for reacting to state changes on the client side, allowing for dynamic visual or gameplay updates. For example, a hook could trigger an animation when a player's health syncvar drops below a certain threshold. Network variables offer a more flexible and modern approach to data synchronization compared to traditional syncvars. They provide enhanced control over synchronization behavior and are generally recommended for new projects using netcode for game objects. Declaring and initializing network variables is straightforward, typically done within your network behavior class. You instantiate them with a default value, and netcode handles the rest of the synchronization process automatically. They enable robust data synchronization between clients and the server, handling various data types efficiently. Network variables are designed to be more performant and offer greater control over how and when data is synchronized, making them a powerful tool. You can control read and write permissions using network variable settings, defining who can modify or access the variable. This granular control is essential for implementing server authority and preventing unauthorized client modifications to critical game data. For custom data types, you can implement iNetwork serializable to ensure they are properly synchronized across the network. This interface allows you to define how your custom objects are serialized and deserialized for network transmission. A key constraint is that network variables require non-nullable types, ensuring data integrity during transmission. This design choice helps prevent common programming errors and ensures that synchronized data always has a valid value. Now, let's see these concepts in action with practical demonstrations in Visual Studio and Unity. We'll walk through the process of implementing RPCs, syncvars, and network variables step by step, showing you exactly how to integrate them into your projects. We'll write example code to declare and utilize RPCs, syncvars, and network variables within a simple script. This hands-on approach will solidify your understanding of how these networking primitives are used in a real-world Unity project. Next, we'll attach this script to a game object in Unity and configure its network object component for networking. This crucial step links your script's networking logic to a physical object within your game scene, making it network-aware. Finally, we'll test the networking code by running multiple Unity instances or builds, observing the synchronized behavior. This will allow us to visually confirm that our RPCs are firing, syncvars are updating, and network variables are synchronizing correctly across all clients. Always encourage server authority to prevent cheating and maintain game integrity. The server should be the ultimate source of truth. Any critical game logic or state changes should originate from or be validated by the server to ensure a fair and consistent experience for all players. Limit client-side syncvar modifications to reduce bandwidth usage and avoid unnecessary network traffic. While technically possible, allowing clients to directly modify syncvars can lead to inefficiencies and potential security vulnerabilities, so it's best to restrict such operations to the server. Use network variables for synchronizing game state and RPCs for actions or events that need to be triggered. This clear distinction helps in organizing your networking code and choosing the most appropriate tool for each specific synchronization or communication need. Choosing the correct network protocol, TCP or UDP, is vital for your game's specific needs, balancing reliability and speed. TCP offers guaranteed delivery and ordering, suitable for critical data, while UDP provides faster, but less reliable, transmission, often preferred for real-time game data like player positions. Optimize network performance by reducing data transmission frequency and payload size. Sending less data, less often, is key to minimizing latency and ensuring a smooth multiplayer experience, especially for players with slower internet connections. Understanding network protocols like TCP and UDP is fundamental for effective multiplayer game development. A deep comprehension of how these protocols handle data transmission will empower you to make informed decisions about your game's networking architecture and optimize its performance. In summary, RPCs, syncvars, and network variables are indispensable tools for Unity multiplayer game development. They form the backbone of interactive networked experiences, allowing players to share a dynamic and synchronized game world. We've covered their definitions, implementations, and best practices, providing a solid foundation for your projects. This knowledge will enable you to build robust and engaging multiplayer games with Unity's netcode for game objects. Explore further by consulting Unity's official documentation and sample projects to deepen your understanding. The official resources are an invaluable source of detailed information, advanced topics, and practical examples to expand your skills. Additional resources like the Unity Multiplayer Networking ebook and netcode samples are excellent next steps. These materials offer further insights and ready-to-use examples that can accelerate your learning and development process. Thank you for watching, and happy networking! We hope this guide has provided you with the essential knowledge to start building your own exciting multiplayer games in Unity.